Imagine trying to route 418 taxis through the sprawling, dynamic grid of downtown Beijing, all at the exact same time. The math is staggering. You have millions of potential route combinations, and every car's choice interacts with and interferes with all the others. To solve problems of this scale, we turn to the most powerful tool we have, the classical supercomputer. But a supercomputer processes information using bits locked into binary logic, either 1 or 0. Because of this, machines process information in sequence, moving one by one. When there are millions of overlapping variables, the data stacks up. Faced with these multivariable problems, classical machines simply run out of time and processing capacity before they can find the most efficient path. Navigating these massive grids isn't a problem a faster supercomputer can solve. It requires a system built on a completely different logic. That system is quantum computing, built on a new unit of information called a qubit. Instead of being restricted to a 0 or a 1, quantum mechanics allows a qubit to hold the properties of both states at once. Think of a classical bit like a flat, stationary coin. It's either heads or it's tails. Now, give that coin a flick. While it's spinning in a blur, it exists as both heads and tails at the exact same moment. In quantum mechanics, this dual state is called superposition. Because of this phenomenon, a qubit in superposition can explore vast numbers of computational possibilities simultaneously. This eliminates the sequential bottleneck. Instead of evaluating those millions of Beijing traffic routes one by one, a quantum system can look at the entire map in a single step. To manage those connections, qubits rely on a second pillar, entanglement. When you entangle two qubits, they become linked. Changing the state of one qubit instantly forces its partner to change as well, no matter how much distance is between them. This link was so foreign to the laws of classical physics that Albert Einstein famously called it spooky action at a distance. But if a quantum computer is looking at every possibility at once, how does it decide which one is the actual answer you need? That brings us to the third pillar, interference. Qubits act as waves, similar to the ripples created by dropping pebbles in a pond. Engineers can manipulate these wave collisions. They use constructive interference to amplify the probability of the correct answer, and destructive interference to cancel out all the wrong ones. By combining superposition, entanglement, and interference, these machines don't just calculate, they filter through every possible reality to isolate the optimal solution. Let's go back to the traffic in Beijing. D-Wave systems used these principles to process the millions of overlapping traffic variables for Volkswagen. The data showed that by optimizing every route simultaneously, the quantum system achieved a 20% reduction in average wait times. Routing taxis is just the beginning. These systems are being built for complex modeling that classical computers can't handle, from simulating millions of molecular interactions for new drugs to tracking the behavior of dark matter. This ability to check every combination at once also threatens modern digital security. Our current encryption relies on math problems that take classical computers billions of years to guess. A quantum machine could potentially identify those private keys in minutes. However, these systems are currently held back by a physical limitation. They are incredibly fragile. Any minimal environmental noise, like a stray magnetic field, can cause the quantum state to collapse. The current technological race isn't just about building larger processors, it's about learning exactly how to stabilize them. Once we can shield these qubits from the outside world, we can solve the biological and logistical challenges that a binary system will never be able to reach.